So first, I would like to express my sincere gratitude to the organizers for arranging this workshop, and also all of you for giving your time to the event. It's really my privilege to start with by introducing the basis of the dynamic universe theory, which I've been working with for the last roughly 30 years now. So let's go to the start. Here we are. The basic assumptions behind the dynamic universe is that we describe the three-dimensional space as a free sphere. Mathematicians call it free sphere, which means that it's a kind of three-dimensional surface of a four-dimensional sphere. So that in order to prevent confusion, I call it free sphere in my talk. DU honors the zero energy principle, which means the balance of the energy of motion and gravitation, which is the key in the whole theory indeed. As prior art, we can find that in fact the idea of both the free sphere and also the zero energy principle has been proposed by several well-known scientists in the past. Schwarzschild pondered spherical closed spheres in 1900. Einstein proposed that the free sphere space in 1917, and in the 1930s, Richard Tolman already pondered the buildup of mass energy against negative gravitational energy, which in fact is just the basis for the dynamic universe. In his lectures on inertia in 1953, Denis Sciama pondered zero energy balance of the total energy and the gravitational energy in space. And in his lectures on gravitation in 1960s, Richard Feynman pondered both the free sphere and the zero energy balance as a great mystery in physics. And in the book he stated, in the lectures he stated, that why should we study physics if the mysteries are the most important things to be studied? So in dynamic universe, when we follow the zero energy principle in the free sphere, the relativity appears as a direct consequence of concerning the energy balance, and also, which is very important, the link between local and the rest of space. And in fact, the dynamic universe is a kind of holistic view of the whole, rather than the local approach, as for example the theory of relativity. Also, it means, as Ari Styrman stated, that for looking for absolute simultaneity, relativity in this approach can be expressed in terms of energy rather than in terms of dilated time or contracted distance. So that's the way of conserving the time and distance as natural coordinate quantities, which are very essential for human comprehension. So it means that DU offers a framework for relativity and quantum phenomena and provides a precise predictions for observations ranging from quantum systems, microsystems to cosmology, mostly in very simple mathematical form. So just a quick look to the documentation of a dynamic universe. The very first documentation came from 1996, and it's completed gradually to its present form. And it's the latest book now comes from 2018, and it looks like this, about 300 pages. And I completed the view by looking the path of the development of present theories by writing the short history of science, and I felt that extremely important for me to see how we have come to the situation where we are today. Okay, in this introduction, I will start with a spherically closed space and the energy built up via contraction and expansion. Motion in spherically closed space, inertia as an implication of the zero energy balance, which shows that how local phenomena then are related to the system, to the whole and to the rest of space, build up of local structures, which leads to a kind of system of nested energy frames, which means that we can define both the local frames and link them to the rest of space through parent frames up to a kind of hypothetical homogeneous space. And finally, as a very important part, which is not a cosmological view, but we can start from Maxwell's equation, we can show that finally there's a very simple connection between Maxwell's equations and Planck equations. So let's continue. Starting from spherical closed space, how we can get into that starting from present view. In the theory of relativity, the fourth dimension is designated the time dimension. However, the line element in the fourth dimension is c times dt, which means meters per second times second. So that although the dimension is called the time direction, it's measured in meters. So we could also say that instead of being 13.8 billion years from a starting point, we can say that we are 13.8 billion light years distance from a starting point in common to every point in space, and that's in the fourth dimension. But practically, that means, geometrically, that means that if all points are at the same distance from a point in common, so we are in a free sphere. But also it means that when we interpreted the fourth dimensions as c times dt, at the moment we are the whole structure is expanding at velocity c. So let's look at the energy balance in such a structure. So obviously the barycenter of the free sphere, mass in the free sphere, is in the middle of the free space, so that we can see that once we interpret the motion, fourth dimension as motion at velocity c, it means that we also have momentum mc in the fourth dimension, which means that now we can interpret the rest energy of matter as the energy of motion due to the expansion. And obviously that's balanced with the energy of gravitation, which arises from mass equivalence at the center here. So for when we then equate the energy of motion and energy of gravitation here, we can solve the speed. And using the best known values for gravitational, of course, gravitational constant, the total mass calculated from the mass density in space and Hubble distance, we get 300,000 kilometers per second, which simply confirms the idea of the expanding free sphere. So what it means that we can consider the whole system as a spherical pendulum starting from very, very large radius in the past. It means that it first gets its motion from its own gravitation. So all mass gets its energy from the gravitation of the structure and build up now the rest energy as the energy of motion against the release of gravitational energy. This is exactly what Tolman was looking for in the early 1930s. So now, after the turning point, we are paying back the loan of energy loan, and so we can say that dynamic universe is just a kind of double entry bookkeeping of energy in space. So let's see how that compares to the present model, which you are all seen with this kind of presentation. When going to dynamic universe, here we first extend the time axis to almost practically infinity in the past, and let the space build up the energy in a contraction here, and now we are on the way to pay it back here. And what is important here, that with this simple energy balance equation, we can get precise expressions to the dynamics of expansion. So we can solve the radius, the velocity, and also it turns out that the time is now less than the Hubble radius divided by c, in order to make that more comparable with the standard view. I have used here the dark energy value 0.735, which is very interesting number, because with this number the time becomes exactly equal to Hubble radius divided by c. So in a way that matches the Friedman solution with the kind of Friedman solution with Minkowski space with constant average expansion velocity c. And by putting the dark energy equal to share equal to 0 here, we in fact get exactly the same kind of profile as we get in the dynamic universe. And in fact, Einstein, the Sitter solution, honors conservation of energy, so that they stated that expansion works against the gravitation of the structure. So it's basically exactly the same as what we have in the dynamic universe. So that we can call that dynamic universe expansion is a kind Einstein-Sitter expansion applied to free sphere space. Okay, let's see what it means in the buildup of energy and let's say the development, the energy balance in space. In standard cosmology, the mass energy and radiation is essentially constant here. I can't put the show of the dark energy here, but as I stated earlier, it's generally accepted that today we have roughly the balance between the mass energy and the gravitational energy. So today we have a similar situation, but in the case of dynamic universe, we have exactly the same. We have the same balance throughout, from the infinity in the past practically, or to the infinity in infinity in the future. And it's very interesting in the sense that we have noticed with James Webb Telescope that the early development of galaxies and local structures has been much faster than expected. So that's the energy available for that galaxy formation. But in the case of dynamic universe, now we have essentially higher energy here for the same. So that's easy to understand that the early development has been very, very fast compared to what it's today. At the same time, it means that c is not a constant, but c is linked to the expansion of space all the time throughout the whole development. So let's look what it means. Sorry. Now start with this. So mass in space has velocity c in the fourth dimension. That's what we notice already. And the rest energy or mass m at rest in space is mc to the second. And we'll find that we little bit need to elaborate that very, very famous equation. and all that is balanced with a gravitational energy. And now it means that any momentum p in space, in a space direction, is associated with momentum p in the fourth dimension. So the total momentum is a kind of orthogonal sum of these two. And here I demonstrate it with this line here. And it means that we immediately get the solution of total energy or total energy of motion, which was obtained by Einstein using the coordinate transformations in his publication in 1905. And now we didn't need any time dilation or coordinate transformation for doing that, but it was a direct consequence of conserving the total energy here. But what the theory of relativity didn't disclose here, that the increase of momentum here is associated with a reduction of rest momentum, and that turns out to be extremely important because the frequency of atomic clocks and physical phenomena in general are proportional to the rest energy in the system. And we will come back to this a little bit more precisely after a while. So let's first look what happens when building up local system in space. We like to maintain the zero energy balance of the energies of motion and gravitation here. So these are the two arrows which must keep it equal. And how can we create motion in the space direction without disturbing this balance? The nature indeed has been very clever in that it occurs by bending the local space. When we can find that part of the momentum in the fourth dimension, the original fourth dimension, it's now divided into orthogonal components, which are the momentum of free fall and momentum or rest momentum in the local fourth dimension, as indicated here. And we get the symmetrical change in the gravitation side, which means that we can express the energy at this point here in terms of the local gravitation, which is expressed in terms of the delta term, which is gm divided by rc to the seconds, where r is the distance, flat space distance from the local mass created. What is very important here is that in fact here we get the energy of motion from the energy of gravitation of the falling object. So we are not bringing any extra energy to the system, which we in fact need when we create motion at constant gravitational potential. Here also I have demonstrated that the same build-up of local centers occurs then in several steps. Let's say that the solar mass here, so that the Earth mass is here, and further on there's the moon mass, which makes a small dent in space. And now the decreasing velocity of light when we approach the mass also gives the gravitational factor to atomic clocks. And let's look how it compares to motion in space at constant gravitational potential here. So that here I have demonstrated the kinetic energy, which is c times delta mc. And what is very, very interesting here, that the part mv, delta m times v, increases the momentum, gives a kind of the relativistic momentum here. But what is the imaginary, the fourth dimension component here is exactly the work we are doing against the gravitation. So the rest energy of a moving object is reduced due to the work done by the motion as central motion against the global gravitation. So any motion in space, in fact, is central motion relative to the center of the free sphere. So in very simple terms, we can now get a quantitative expression to the inertial work. And in fact, the inertial work is just the work that reduces the rest energy of the moving object and also makes the atomic clocks run more slowly when in motion. So by combining the gravitational term and the motion term here, we can see that the rest energy of an object at gravitational state delta and motion state beta, which is v divided by c, gets this simple form. And we can show that the frequency of atomic clocks is directly proportional to the rest energy, or more precisely rest momentum, and we get the equation for frequency here, which compares to Schwarzschild's solution for dilated time due to gravitation and motion. So these two equations are very closely in near Earth circumstances. The difference between these two equations comes only in the 18th or 20th decimal, so that experimentally we can't find out the difference between these two. But what is very, very important well, let's first look how that compares to the general picture of space. Now we don't call this space-time, but we call this space a four-dimensional view of space, so that space is bended in the fourth dimension close to the mass centers here, and we have then several dents here around each mass in the system. So finally, combining these, we can now build a system of nested energy frame. So each time we create a subsystem, it means also that we bound a certain amount of energy at each level. So the lower we are in the chain here, from hypothetical homogeneous space to local grooves, Milky Way, solar system, Earth, accelerator, ion, the less we have energy available for local actions. And then we can write the energy equation in a closed form here. And that follows then the clocks. And finally, using this equation, we get exactly the expressions which in practice are used for different experiments. Laboratory experiments are related to the rest clock in the lab only. The first time the theory of relativity was tested in motion, almost in space, in commercial airplanes, showed that we can't use the reference at the airport, but instead we need the reference in the Earth-centered inertial frame, ECI frame, which is a reference clock at rest, far from the gravitational effect of the Earth. And following this, we get the GPS satellites and so on. And what is important now, that we can connect all these experiments together. And the further we go, the more references we need. Here we need a rest clock in the solar system for comparing clocks in the Mars lander or Pioneer spacecraft far from the sun. Okay. Now, very important question is that what happens to the very old, very important, historically important experiment for the velocity of light, which didn't look like summing up to the velocity of the observer. In the DU framework, the velocity of light is locked to the local velocity of space in the local fourth dimension. So you can think here that velocity, the local frame is locked to the mass equivalence, which in a way follows the motion of the local frame when it moves at constant gravitational potential. So we come to a very interesting comparison here. What was the choice in 1905? Newton equations or universal time and distance. So that was the choice Einstein had to do when developing the theory of relativity. Newtonian equations were empirically verified and was looking as the basic law of nature. So his choice was here to offer the universal time and distance, which led to the time dilation and length contraction. In the dynamic approach we have made here, when we recognize the motion of space itself and add that to any motion in space, we can change the balance here. Now we know why Newtonian equations as such are not valid, because at that time, also at the time when special relativity was formulated, it was generally accepted that space itself must be static. And once this is not the case, we can understand why the equations shall be rewritten. When we follow now from this standpoint the development of Newton's second law, F is ma, originally this is the form. Einstein added the effect of longitudinal mass here, and in fact we get directly the same results by taking into account the motion of space. And what du adds then is also the effect of local gravitation, and not only that, but also the effect of the motion and gravitation with the parent frames we are working with, and that comes from the basic energy equation here. So very shortly, comparing these two approaches, observer-oriented description based on kinematics and metrics, we see we can describe the behavior of clocks by with reduced local flow of time, and here we by a system-oriented holistic approach we can find out that local gravitation and motion reduce the rest energy of oscillation electrons in the clock. And here we can see delta E divided by H. And there's a very important point which I still like to introduce in this introduction, is that we can conclude that there's one C included in Planck's constant. When looking at the history, I found that in the final comments of his Nobel lecture by Wilhelm Wien in 1911, he stated that the Planck theory has not yet brought into definite form. In science, the demeaning idea often comes from an entirely different direction. Investigations in an entirely different field often throw expected light to the dark aspects. And let's start from here. We are used to Planck's equation in form EHF. We can equally express the expression in form E is h divided by t, where t is the cycle time. And now it sounds very natural to look that that physically the latter form can be interpreted as the energy carried by a cycle of radiation. And so let's switch the question to a radio engineer. What's the minimum amount of electromagnetic radiation emitted by an antenna in a cycle of radiation? So we start with standard formula, which you can find in any physics textbooks. The only thing we need to do is to a little bit rearrange the parameters here, the angular angular frequency to frequency and wavelength, and we can get the power, emission power, in this form here. So now this number of electron, the length of the dipole related to the wavelength emitted, and this is a geometrical factor of a Hertzian dipole, 2p to the second, 2p to the third, electron charge to the second, vacuum permeability, c and f to the second. And now we are interested in energy per cycle, which means that it's P times T, or P divided by D, and we can now get it into the form where we have the antenna parameters here, and then F as the frequency, and by looking the minimum amount by putting N1, the number of electrons for one electron oscillating in the system, we get one, and the geometrical factor close to 1 to demonstrate an point diode or a diode radiating equally to all directions. And now we can see that here we have also C, and here we have H. Exactly now it's related to the electrical constants E and mu, zero, and here we have C and F. And now we introduce the intrinsic Planck constant, where we remove C, which means that we can give the Planck equation in form E is equal to h0 divided by lambda, which is kilograms to the c to the second. Or in terms of wave number, h bar 0 times k, the wave number, times c to the second. And we can also find that vice versa it works, so that now the energy of the rest energy of a particle is h0 divided by Compton wavelength. So that we get very similar results here. And also what is very interesting, that the fine structure constant now appears to be a pure numerical or geometrical constant. So it's not related to any other physical constants. And also we can express now the H0 in the simple form, but I jump over here. And importantly, now all the energies here can be expressed in similar form, so that they all are in a form that h for bar 0 times wave number times c. And so it will be very easy now to follow the conservation of energy once we have these equations. I finish my talk with this slide, with the last slide here, which gives a general picture of the two approaches. So for historical reasons, the development has started for Newton's equations, which has force as the basic quantity, and so the basic definitions starts from force, and then energy becomes a derived quantity. In the dynamic universe, we start from the energy equations, and we can then derive force as the gradient or potential energy or time derivative of momentum. And we can essentially now simplify the whole structure so that we can get cosmological predictions directly from the zero energy balance in space, instead of going through theory of relativity. In fact, relativity itself, relativity is included in the basic structure of dynamic universe. So we don't need a separate relativity theory at all. And what becomes very important here is that quantum mechanics, by rewriting the Planck's equation, is h0 bar h bar 0 times square to the second. We can describe particles as mass wave resonators, so that we can understand the connection between particles and waves. Okay, so this was my story for the beginning, and now
Thank you.
we are ready for discussions or questions.
So we've got 20 minutes for people's questions, and any questions and clarifications or so forth.
Yeah, first, may I say that I guarantee that we are not changing the reality or the universe itself. We are only looking at from a little bit different direction, from a different viewing angle, so that there's no risk of changing the world.
So I was wondering, with the bit about special relativity and GR and reducing the local flow of time, and the dynamic universe, reducing the energy of the particles. If you see time as the measure of motion, are those two things necessarily different? Because if the particles are oscillating with a lower energy, then there's less motion and therefore less time happening.
Sorry, can you focus the question? Yeah.
Yes. So you said that in special relativity, the idea is that gravitation reduces the local flow of time, whereas in the dynamic universe, it reduces the rest energy. Gravitation is reducing the rest energy of the particles.
Yeah, it's a choice between if we choose constant defining constant velocity of light and constant rest mass, then we need time and distance as parameters. So the choice here side is that we accept time and distance as universal coordinate quantities, and in that case we can see that the relativity can be expressed with mass, and the velocity of mass is a function of motion, both local motion and all the motions in the parent frames, and the velocity of light is a function of local gravitational state, and also taking into account the gravitation of the parent frames. So that's the change, that's the difference.
I was wondering if, on a conceptual level, you get this idea that time is the measure of motion. That time is simply.
But how I understand time, it's a coordinate quantity. So it's not the physical phenomenon or quantity. That's something. It's a reference for measuring velocities or rates of processes and so on. So that in dynamic universe, the rate of the clock is changing, and we measure the rate with a uniform coordinate quantity time. So then we can choose then what is our reference unit of time. Now S is second is fixed to the frequency of cesium clocks, and in order, if we look that from the dynamic universe perspective, we should define where the clock is and what is the status of the Earth in its orbit, because the elliptic orbit also changes the frequency, and that's something that has been clearly observed when we compare the clocks with distance pulsars that gives a independent reference without the annual change. Yes.
Let's say that we take the twin stars.
Yeah.
With the standard thing. Say to undergrads, you've got Alice and Bob, and they're twins.
Yeah.
They're both. Alice goes off, comes back again.
Yeah.
She's a different age because of boosts that she has undergone. Does the dynamic universe have a different perspective on that?
Oh, of course, absolutely, yes. Because there is no twin paradox, because we are not looking the velocity relative to the object we are looking, but any velocity is related to the state of rest in the local frame. So that velocity perhaps is not the basic property of motion, but the kinetic energy. So the state of rest is the point from which we have given the energy for the motion. So that there is no twin paradox, because any location, any state of motion and gravitation determines the rate of the clock. So the paradox, the twins, certainly, if they are moving fast, the process of any physical processes are slower. So in that sense, we can conclude that the aging proceeds more slowly, but they use the same time as somebody at rest. So it's
So more physical processes happen to Bob.
We can conclude that any physical processes have the rate determined by the state of motion and gravitation. So that each one of us, our physical processes also are dependent where we are, if we are on the Earth, on the satellite or other planets, so that the rate of our processes may be different.
So it sounds like the way that you're using the word time is different to proper time.
We don't need the proper time and coordinate time definitions at all, because time is time.
Uh-huh.
Time is a universal coordinate quantity, like distance. And
would we have a different word then to describe? Let's say, Alice counts the number of ticks that she's heard from her cesium clock. Bob counts the number of ticks on his cesium clock.
Okay.
They come back together. You agree that their numbers are different?
Oh, certainly, because that's very standard. Because, for example, the GPS satellites, the clocks in the satellites, they are matched. They are matched to the Earth second, so that they are counting a higher number of cycles for a second. Because the frequency of the clock is higher. So let's say that during 1 year calculated from astronomical observations, the satellite clock has been given more cycles. Total number of cycles in the satellite clock certainly is higher than the clock on the Earth.
Okay. Yeah.
Oh, sorry.
Yeah.
So, if I understood one of your slides correctly, you were saying...
Sorry, I have a little bit hearing problem. I use my hearing...
That your slide correctly in relation to local clock time. So there was a difference in the formula. So, is this better?
Yeah. Okay,
Yeah.
that's a little bit better.
Okay.
Thank you.
If I understood your difference between the dynamic universe clock time formula and the standard model clock time formula. You were saying it was unobservable in Earth's gravity, right? Because of the difference would be of the attosecond.
In fact, I don't have time formulas at all. I have formula for rate of a physical process, like atomic clock. So that makes the very basic difference indeed.
Yeah, so my question is, if you had a strong field to observe, such as a merging black hole, would you expect to be able to detect the difference?
Yeah, in fact, that's a very important question, because deriving the celestial mechanics at extreme conditions with the dynamic universe, which is based on the conservation of energy, we can get stable orbits down to the critical radius. So in fact, we can find that there are slow orbits near the critical radius that maintain the mass of the black hole. And as we know, there are no stable orbits below 3 times Schwarzschild critical radius in the standard formulation. And my analysis for that difference, where it comes from the difference between conservation of energy and the equivalence principle. So that as you could see that in free fall, we don't increase the energy of motion, the total energy of the falling object. But when creating motion at constant gravitational potential, we need to insert extra energy or extra mass as the substance for the expression of energy. And from that difference, it looks to me that comes that is the problem in standard formulation, that if we can see that the velocity of escape velocity, the orbital velocity exceeds the escape velocity at 3 times Schwarzschild critical radius. And we can avoid that when we follow the conservation of energy.
So would you expect a different waveform from the radiation and gravitational waves as observed by LIGO?
Also, I derived a formula for gravitational gravitation. I get practically the same formula as Taylor, the famous Taylor formula. The only difference was the effect of eccentricity. So that in the du formula, the gravitation or the energy emitted to gravitation goes to 0 at circular orbits, which is not the case in the Taylor formula.
Interesting.
Yes, I have some slides on that, but we can come to that later on. Yeah. So that in general following the energy, zero energy balance, the conservation of energy, we can essentially simplify the equations, and it will be even more obvious when we go to the predictions in cosmology. And it's easy to understand such things like cosmological time delays and so-called cosmological time delays, because phenomena itself have been running faster in the past, but nevertheless we observe them like being extended. And there's a very clear explanation for that. Yes.
Any other questions?
Yeah, thank you for using the microphone. It makes my life much easier.
You can hear me okay?
Okay, perfect.
Marvellous.
Yes.
Okay, really dumb question to start off with.
I like those, yes.
Great. So going back to the days when I had to pay attention and learn things, I remember being taught that the speed of light was the invariant.
Sorry, what is it again?
The speed of light is a fundamental invariant.
Okay, yes.
But now you've jogged me that that's not the axiom. The axiom is the invariant.
No, it's not axiom. No, it comes, the speed of light, we can show that the energy balance demands that the maximum velocity in space is exactly the velocity of the expansion. So that all the time, although the absolute value of the expansion velocity and the velocity is changing, those two are linked together. firmly linked together. Yes.
So then the question is, if you are developing new theories,
Yes.
do you require that the speed of light is invariant, or hope that that drops out every single time that the sophistication advances?
If I understand your question now, once again, time is just a universal coordinate quantity, and everything is explained via the status, energy state comprising the gravitational effect and an expansion effect on the velocity of light, and the effect of motion on the rest energy. So that from these parameters we can build all the predictions. But in most cases, when accepting the different view here, the numerical results in most cases are very much the same, almost the same. In cosmology we have some differences, but we will come that to later on.
Any other questions?
Yeah.
So you have a very preferred coordinate system, right? So
Yes.
unlike GR, you have a really preferred
Yes,
coordinate
yes.
system. So then do you get some predictions which are different from GR? Like what about say simple things like perihelion precision of Mercury or
No, one that I already mentioned was in celestial mechanics. We get different prediction for the escape velocity and orbital velocity as what we have in Schwarzschild solution. But in most cases, it's typical in standard physics that the observations are more or less matched to the predictions are matched to the observations, if necessary, finding new parameters. So that in that sense, it's sometimes very difficult to make a fair comparison between the theories, because in dynamic universe, I don't like to use any additional parameters which are not based on the basic structure of the theory.
and your gravity is also not a tensor quantity here, right?
Is what?
Because of your preferred frame. So gravity is not described by like a metric, right? So then how well could you match? You said
The gravity start that in this idealistic case we simply have the very original Newtonian formula. But as soon as we have the local structures, they are certainly modified then, because we have to take into account both the local and the parent frames and then the total. So that very importantly in dynamic universe, any local object is the state is linked to the rest of space through the hypothetical homogeneous space.
Okay. And last question is that when you have this energy conservation, right, from zero energy totally,
that's the key. Yes.
So so you need some coupling to conserve the energy also, right? So energy must go from gravity to the matter through some coupling. So do you have a Lagrangian or something which couples the two?
Yeah, very much indeed. So that's question. Basically, most physical processes can, at certain level, described as the interplay between potential energy and motion, energy of motion and potential. That was the way Maxwell was derived his Maxwell equations, and that's the principle. Finally, with roots to Aristotle's entelecheia, where natural trend is to make potential actualized, to get potential actualized. So that in the simplest example is the pendulum, so that it gets motion by releasing gravitation and may put it back.
Okay, thank you.
And very importantly, mass, also I strictly follow the dimensional analysis due to maybe my technology background, so that it means that mass can't be considered a form of energy. Mass, I have called mass as the substance for the expression of energy, because mass is available in some form, in any form of energy. It's not readily seen, but as we remember also already Poincaré and some others saw that there's a kind of electromagnetic mass also in radiation and other electrical phenomena.
I'll give you 2-3 minutes. Anybody wants a coffee or some water? Yeah, while I'm getting ready on the